I want to thank the Minnesota Local Technical Assistance Program, the LTAP program, and the Short Span Steel Bridge Alliance for this opportunity to present Simple for Dead, Continuous for Live Designs for Optimal Performance. And I hope that the audience takes this information. It's been presented in a couple forums, so if you've seen this before, I appreciate you just sticking around and listening. I might have a new thing here or there that you didn't hear before, but I appreciate the opportunity, and we'll go ahead and get started with this presentation. So first off, I want to this kind of little roadmap of what we're going to talk about. What is Simple for Dead, Continuous for Live? How did we begin using Simple for Dead, Continuous for Live? Wasn't an edict from me or any of my staffs to say that we shall be doing this, but we'll get into how we came about doing this. So why bridge bundling and a summary of previous projects. I'll talk about our specifics for the Fixing Access to Rural Missouri, our farm bridge project. This was a design build bridge bundle, but we also got a federal grant. And so if you're writing grants, you always got to have a catchy acronym. And so Fixing Access to Rural Missouri, the Farm Bridge Program, is what we use there. What have we done since the Farm Bridge Project? We'll talk about that. And then what's next? So let's get on into what is Simple for Dead, Continuous for Live. This was developed at the University of Nebraska-Lincoln by Dr. Adarad Azizan-Amini and his colleagues there, graduate students and so on. It was funded by the Nebraska Department of Roads, and the work took place in early 2000s. I show a picture of the cover of that research report that was submitted to the Nebraska Department of Roads. As you can see, it's dated July of 2005. Additional documentation for the procedure, Simple for Dead, Continuous for Live for steel bridge systems is in the AISC Engineering Journal, second quarter of 2014 and the third quarter of 2014. So volume 51, numbers 1 and 2 are both dedicated. And you can see on the slide there the different papers that are in this journal. And at that time, Nebraska did some bridges as well. So Simple for Dead for Continuous for Live. So basically what we do is we can do multi-span bridges using simple span wide flange beams, plate girders, or box girders, place them on the supports, simply supported, and then make them continuous when we cast the deck, like we've been doing with that other material for since the late 50s, early 60s for live load. So what does this allow? We'll get into that as well as we go through the presentation and why is it advantageous to do this. So just for reference here, Missouri, we are in the heartland here. Minnesota is directly neighbor to our north with Iowa in between us, but just for reference, here we are. And how did we begin using them? Well, if we look at our national bridge inventory from 2025 every year, I'm sure you all know that states have to submit their bridge inventory to the Federal Highway Administration by March 15th of every year. We usually try to do it the Friday before. We have 10,427 bridges on our state system. And if you look, that's the top left map. And poor condition bridges, we've been focusing on with asset management approach to reduce the number of poor condition bridges. And it's also one of our tracker measures that you can find on our website, modot.org. But as you can see with the bar chart there, over the course of the last 6 years, we've reduced the number of poor condition bridges from just under 900 down to 752. The map in the bottom left there shows where these are located. They're throughout the state, no discrimination from urban areas, rural areas, wherever. The insets on the map are some of our more urban areas of the state. Um, so we've been focusing on the poor condition bridges, and you may say, well, if you just throw enough money at it, you can get rid of all the poor condition bridges. But we also look every year at the average number of poor condition bridges we add to this list and the number that we remove from this list. So over the last 5 years, the average of bridges added to our poor condition is 94, and the number of bridges removed is 123. So we gotta do almost 100 bridges a year just to break even, and to make this number move, in a positive direction. We got to do more than 100 bridges. When you got 10,400 of them, and their average lifespan is 50 to 75 years, you got to be replacing a lot of them or rehabbing a lot of them to keep making progress here. So I'll start off with the history of our design build law, and this is getting to the fact of how we came about using this simple for dead, continuous for live concept. So our Missouri legislature first allowed in 2004 in the state statute section 227.107, and I give you the web address there for that state statute. It allowed 3 design build projects. And so the new I-64 was 12 miles of urban interstate reconstruction in St. Louis, Missouri. Uh, this was started in 2005, basically. And so one year we closed 6 miles. We closed an interstate that had 120,000 vehicles a day. Um, Redid six miles, all of the overpasses and all that in that corridor. And then the next year we closed the other 6 miles, and did that work. The KC Icon was replacing a bridge over the Missouri River that carries Interstate 29 over the Missouri River in Kansas City. And then the Safe and Sound Bridge Bundle was our first bridge bundle. And we started out, we were going to do 800 bridges with this project. We found out we didn't have a bridge in a couple counties, so it became 802 bridges. But the design build portion after our first procurement try, the design build that failed because it was design, build, finance, and maintain, and it just became too expensive for that. So the design build portion was 554 bridges in the Safe and Sound Bridge Bundle that was throughout the state. After we did these 3 trial projects, the legislature approved of our execution of design build and expanded our capability to do that, and that took place in 2012. If you go to this web address, you'll probably see the 2012 bill, but you can look at the revisions over the course of years by clicking links on that page. So now it's limited to 2% of the number of our STIP projects per fiscal year. And we do on the order of several hundred projects a year. So 2% of that, we're limited to 8 or 10 design build projects per year. Typically, we do about 3 design build projects per year. But what this legislation says is you must pre-qualify or use a 2-phase procurement. And so the first phase of that procurement is we'll put out a request for qualifications. And this is an opportunity for contractor and consultant teams to form and say, we're qualified to deliver this particular project, and these are our people that we're going to put on this project, and here's our history of work similar to this, and so on. And so those come into MoDOT, and our design build project director that would be assigned prior to a particular project, and his team or her team would evaluate those requests for qualifications. If there are more than 5, we would shortlist that down to 5. And the legislature requires that we have at least 2. So after the RFQ stage, we have a short list of 2 to 5 design build teams that want to compete for this particular job. And then we do the request for proposals as the next step. So I think around the country, we're known as being very good at doing design build since we've been doing it for more than 21 years. We've had 32 awarded contracts worth over $4.7 billion. Nine are currently under contract worth over $2.5 billion, and two projects are in procurement worth $875 million. One of them is the Improve I-70 that is from Columbia, Missouri to Roachport. It's about a 13-mile stretch from the center of the state westward towards Kansas City. It includes about 4 or 5 miles of urban city. Columbia is a city of approximately, 125,000, and the Boone County area has probably got 400,000 people in it. And so the Forward 44 is a project in the Route 44. It follows the historic Route 66. The Improve I-70 project was awarded by the commission on December 3rd. It was $425 million. The other one is $450 million. And we're negotiating with the apparent best proposer on the Improve I-70 to get the contract finalized. We've done 8 design build bridge bundles that improved over 700 bridges. As I mentioned, the first one did 554. Most of the others have done anywhere on the order of 18 to 20 up to the Farm Bridge program had the opportunity to do 41, but we'll discuss that. And typically on these design build bridge bundles, we do a fixed price variable scope or best value approach. And we think we've able to realize an additional 35 bridges improved because of that approach. And I'll kind of describe that as we go here. So what do we see as the benefits of bridge bundling? We can maximize the scope for a fixed budget. And if there are any consultants out there, I'm sorry to say this, but we can control the design cost. It seems that the contractor partners can squeeze the design consultants a little more than we can. And these bridge bundles, we're putting a lot of them, as you'll see in the Farm Bridge program, a lot of similar scope, so there can be some efficiency in the design as well. Once you do a 3-span, simple for dead, continuous for live, and you do 25 of them, you get pretty quick at that. Promote innovation, and this is probably the biggest thing, and the reason for this presentation is because, as I said earlier, there was no edict from the state bridge engineer or anybody in my office that said this project shall be simple for dead, continuous for live steel bridges. And then lastly, the speed of the delivery of project. Once we get these under contract, typically, the design phase is ongoing while construction is starting as well. So I have the 8 design build bridge bundles that we did. The first one, as I already mentioned, Safe and Sound, 554. The Columbia I-70 bridges, this was a number of bridges over I-70 and on I-70 in Columbia, Missouri. I think there was maybe 10 or 12 bridges there. I-44, this was in the southwest part of the state, the Project Bridge Rebuild. And as Dr. Barker mentioned, Short Span Steel Bridge Alliance, plate arches and so on. This bridge had a unique situation where 2 bridges on I-44 main line over local public agency roads were replaced with steel plate arches. And so that was an innovation for that particular project. Boot Hill Bridge Bundle was on the order of 20 bridges. The Farm Bridge replaced 31 bridges, and we'll go into the details of that. The I-44 corridor bridge bundle is also in southwest Missouri. And Interstate 44, as I mentioned, follows mostly the path of the historic Route 66. Northwest Bridge Bundle is underway. In 2026, that'll be finished. And Casinger Bridge Bundle was just awarded earlier this year, I think in September, I believe it was. but another bridge bundle in the southwest part of the state. So 8 bridge bundles that we've been doing. Not all of these have used the Simple for Dad, Continuous for Live. The Farm Bridge program has in the Northwest Bridge Bundle, and we're waiting to see what the contractor comes with the Casinger Bridge Bundle. But those are the reasons we do design build bridge bundling. Those 4 are the highlights basically. So let's get into the Farm Bridge program itself. So as I said, fixing access to rural Missouri, you got to have a catchy acronym when you apply for a grant. We identified 41 rural bridges in northern Missouri. The map of the northern part of the Missouri is shown here. The thick black lines here represents the district boundaries. So the Northwest District is here. It includes St. Joseph and a lot of rural area. The Northeast District is here. It includes Hannibal and a lot of rural area. And so the 41 bridges are identified. And so what criteria did we use to select these bridges? There's one down here in Warren County. Most of them are up here. But the 4 criteria were they had to be in poor condition, right? We're trying to improve our overall asset by removing poor condition bridges. They needed to be weight restricted. So, load posting 20 or 25 tons, something like that. 1 lane, but carry 2-way traffic. We still have a lot of bridges. I say a lot, but not 1,000, but a number of them that are 1-lane bridge, but have 2-lane roadway on them. And lastly, on timber piles. So many of these bridges were built when, the substructure was, 6 40-foot creosoted timbers, right? For the intermediate bents and the end bents. So those were the criteria we used, 41 bridges. And here's a picture of some of these. Top left there, you can see timber substructure, substandard, barrier rail, just general deterioration of the deck where the curb outlets are. We were talking earlier about Minnesota and Wyoming, where Dr. Michael Barker's at Wyoming and Natalie's obviously in Minnesota, and temperature. Missouri gets pretty frigid too, and we put a lot of salt on the roads. So, this is some of the deterioration you see with that. Down here, bottom left, we have a plate. The deck is such poor condition that, sometimes the fix is put a plate over the hole. Top middle, deck repair, full depth deck repair, leave the forming in place because you may need it later. And then single lane on a 2-lane roadway here is the bottom right picture. And then top right is just another picture of a deteriorated farm bridge program. So all of these were on the program. These are not all the same bridge, but they've all been replaced at this time. So on this solicitation, we had 3 proposers, 3 teams. One team chose primarily to address it with precast structures, precast concrete. The Lehman Construction Company, Wilson and Company, Lehman Construction was obviously the contractor. Wilson and Company was the design consultant that was teamed with Lehman Construction. They chose to use 25 Simple for Dead, Continuous for Live structures. And then the third team had a mix of concrete structures and steel structures. The best value proposer, out of the 41 structures, 31 of those structures were replaced. And over here on the right-hand side, I show a list of the bridges. And so they're not numbered 1 through 31 because there were 41 to start. And so here are the bridge numbers out of the original 41, the span lengths, skew, and the W shape that was used to construct these. So what we got, as I said, and then the Wilson Company, Lehman Construction Company gave us 31 bridges. I think the other 2 proposers gave us 30 of the 41. So that's how part of the scoring was how many can you replace, and then there were other factors on long-term durability, those types of things. So 31 structures replaced, 25 of them simple for dead, continuous for live. 3 of them were just single span steel structures, and 3 were RCB reinforced concrete box culverts. So as you can see, some of these bridges are pretty short overall length, and they evaluated the hydraulic need and decided reinforced box culverts would work for 3 of these structures. One of the things that was a great value and gave them some points on the durability, as I said, is these were low maintenance steel structures that allow for future redeck and rehabilitation. A lot of these old steel girder bridges, we do a redeck because maybe it's a poor condition deck, but the sub and superstructure are in fair or even good condition. The Lehman Construction Wilson and Company, they gave us an additional 2,300 square feet of existing bridge deck replaced. The ADT for the routes that they included had the highest average. They're rural bridges. I think the ADT of the most trafficked bridge was on the order of 1,500 vehicles a day. Some of these were on the order of 100 to 300 or so vehicles per day. The highest average benefit cost ratio of any proposal, as I said, we got one more bridge replaced with this team than the others. But anyhow, you can see these structures. There's W12 there, W14s and W16s, all the way up to W24s. So, well, those are pretty shallow. Here's what it looks like on the construction. We allow the use of stay-in-place forms for the deck forming material. This one you can see is a skewed bridge, but the detail of the girders are detailed square. And if you look at the little plan sheet clips here, this top detail shows the compression block. So at the intermediate bends, obviously you're going to have negative bending, compression on the bottom, tension in the top. So the compression blocks just bear against each other, and that's this 3x3 steel block. We put holes in the web because reinforcing steel gets fed through those for the face of the intermediate beam caps. At the end bends, you'll notice here we put shear studs, 3/4 inch diameter shear studs at the end bent. So this is that end bent number 4, so to speak. So anyhow, there's the a picture of what's going on before the deck steel is placed and so on. We also have a detail that we asked the contractor to pour a little bit of the concrete in the intermediate bends and at the end bends to kind of lock in the girders before we pour the whole slab. There's a thin sheet here that you can see on the plan sheet, and you can see it here in the concrete. And the thought there was it's going to crack here, so let's form the crack with this sheet. In future ones, I think they didn't even put that in on the Northwest Bridge bundle and so on. But here you can see in the stay-in-place forms, this one is obviously square to the skew to the roadway. But in the stay-in-place forms, we use the styrofoam to fill the fillets of the corrugated or the corrugations so that we're not adding additional dead load. But there's the negative moment steel and so on. So why do we use the simple for dead, continuous for live? As I said, eliminates the use of traditional field splices. The simple details make steel much more competitive, and I got a slide or two from our friends at DeLong's who fabricated this. We'll talk about that. The fabrication AISC certifies bridge fabricators in 3 categories: simple, intermediate, and advanced. If you're doing a big fancy deep plate girder that's curved and so on, you probably need to be advanced certified fabricator. If you're doing these types of bridges, it's the least rigorous certification, and it's simple bridge. What was beneficial for this project was the shallower superstructure. So we didn't have a lot of money here to raise the roadway grades approaching the bridge, and we wanted to improve hydraulic conditions if we could. And so these, if you look at this top picture here, W18 by 158, it's 60-foot span length. The beam is 19.7 inches deep and it weighs about 9,500 pounds. If we were to use that other material, a type 3 MODOK pre-stressed girder at 60 feet, it's 39 inches deep and it weighs about 24,000 pounds. So the lighter beam weight allows the contractor to eliminate heavier cranes. Some of these can be picked with a track hoe, with a chain on the bucket of a track hoe or something like that. Set them real easy. And then the shallower superstructure, like I said, was mainly for hydraulic consideration and not needing to raise the roadway grade to accommodate a hydraulic opening. Here are the pictures that I borrowed from my friend Gary Wish at DeLong's Inc. And he talks about the benefits of these types of simple bridge fabrication. And the fact that it was a bundle and they got to build 25 of these, he said the first one they probably wouldn't have made money. The second one they would have broke even. And on the next 3 through 25, they got really good at doing these. But farm bridges, they were not plate girders. They were all rolled shapes, as I already showed. So there's no need to cut the flanges. So you don't have to do this operation in the top left. You don't have to shop weld flange plates. And so that's a top right picture here, doing a complete joint penetration weld, and then you've got to do non-destructive testing on that and all kinds of things. There was no camber to cut on the web plates and no flange to web welds, so you don't have to do this operation here in the middle left. You're not making bolted splices, so you don't have to do this operation on the middle right. And full assembly is not required on these. They're pretty simple, so you don't have to do this on the bottom left either. And so that the fabrication efficiencies made it such that the contractor could win this job and deliver, like I said, one more bridge than the others because of these efficiencies. Here's a little bit more. The farm bridges were rolled beams. I took this picture in Steel Day in September 2010 at the Nucor Yamato plant in Blytheville, Arkansas. So rolled beams, you cut them to length here with a bandsaw, and these are you attach the diaphragm connection plates. You attach the end blocks shown in these, the end plate and the end block, and then you install shear connectors shown here in the bottom right. So as I said, DeLong's, after the first couple, got really good at doing this and could do it very quickly, and that saves money, obviously. So the farm bridges were originally going to be weathering steel, excuse me, but from what I understand, the weathering steel was not available at a steel service center, and they would have needed to get these in a rolling schedule from the mill. And so that was going to take too long for the delivery time. So they just went with grade 50 and chose to hot dip galvanize them. These are, I took a picture from the American Galvanizers Association. These are not the farm bridge girders or anything, but this is from their showing the benefits of galvanizing. And this kind of looks like the end blocks of our farm bridge girder, so I threw that in there. But anyhow, because of that scheduled delivery time on getting members from the Steel Service Center, they just went with regular 50 grade steel, shot blast them, send them off to the galvanizer. And so we've got galvanized beams here. So let's look at how you build one of these things. The Lehman Construction Company was pretty innovative. Of course, you got to take down the old bridge that's there. And so they used the girders that were there as a template to drive their pile. And so you can see, excavate, get ready, survey where you're going to put the pile. They've got the template there ready to drive the pile. After you've driven the pile, and for the last probably 10 to 15 years, we've been galvanizing the pile. H pile that we use down to the scour depth. And generally that may be, 20 to 40 feet. If you got a 100-foot pile, we'd allow the contractor to drive the first, 50 or 60 feet of black steel pile and then weld on a galvanized one for the top. But so they've driven the pile there. They pour a leveling pad and they're getting ready to form the back wall and indent of this structure. Same thing for the intermediate vents. You see they got a template there for the six piles to hold up the intermediate vent. Forming the intermediate vent, again, galvanized piles there. We've been having issues with corrosion of pile at the ground line and also corrosion of pile at the beam cap pile interface. And so, like I said, 15 years ago or so, 10 years ago, we went to galvanized pile. Here you see that they've, removed the formwork for the intermediate vents. Started to set the girders in the far span there. You see 4 girders. All of these bridges had 24-foot roadway, 7-foot 4 girder spacing, and some diaphragms that were bent plate or channel diaphragms. So pretty simple to put together. You just set them on the vents, as I said, in simple spans. Here you see them picking and setting girders. Obviously, this wasn't a trackhoe. This was a bigger crane, but this was a rubber-tired crane instead of a big track-mounted crane that may be necessary to place girders of that other material. Here you can see one that's basically got all 3 spans set up there, and you go, well, wow, look at this. They just set the beams right on the piles. This was another in the design build. We allow approved alternate standards. So if some other states do this type of thing, the design build contractor can propose that, and we'll look at it. And initially we thought, well, no, but then we set big plate girders on girder chairs as well. So this is kind of similar to that. But what happens is this all gets formed up and the whole thing gets encased in concrete. You can see the shear studs, as I said, at the indents at the end of the beams. And so this channel at the top of the pile gave them a little bit of flexibility if the pile wasn't in exactly the right condition space. And you can see here it's maybe off by an inch or two. But so that was the next step of setting all those up. Then, as I said, fill the indents and the intermediate vents part way up with concrete. And so they did that here to restrain the rotation of the girders. Then cast the deck. Barrier curb has not been put on there yet. Here, the barrier curb has been slip formed and added. We use our typical barrier is a single slope, 42-inch high barrier. We call it a type H, but anyhow, it's 42 inches. If we have sight distance issues, we can use a 36-inch barrier. So here are a couple pictures of the completed farm bridges. As I said before, we've got galvanized girders, galvanized piles, no joints in the bridge, slab drains to get the deck drainage below the, we typically do 9 inches below the bottom chord. And so here you can see slab drains along this bridge. 24-foot wide roadway. Here's a spray coop going across there. I think they took this bridge picture just because the farm acronym, there's some farm equipment going across the bridge. When you have girders that shallow, you do have an overhang concern or twisting of the exterior girder when you use these typical cantilever form brackets. So you got to be understanding of the stresses that this puts into the girder. Obviously, this puts a lot of torsion unless you brace these very well. And so on some of those, they chose to use a needle beam type system here where you attach it to the first interior girder and have Dewey dag rods holding it to the exterior girder, and then you support your bid mill, screed rail or whatever machine on this. And so this forming may be a little bit more complicated than just using these typical overhang brackets, but it eliminates the concern of torsion on this exterior girder as much. So what have we done since the Farm Bridge program? Well, the Northwest Bridge Bundle, essentially the carry on of the same contractor got this program, and they did 9 superstructure replacements with Simple for Dead, Continuous for Live, and 15 full bridge replacements. So I just got this here is oh, I don't know which county it is, Knox County, I think it is. NO 714. It was a superstructure replacement. Around here, we call these U-beams or bathtub bridges. Essentially, they were lightweight concrete, precast U-shaped beams that were set side by side and tied together. A very shallow superstructure, as you can see. But the lightweight concrete was kind of porous, and these weren't pre-stressed, they're just reinforced. And so you can see the concrete spalling off after chlorides got to the reinforcing steel. So this was just a superstructure replacement. The beam cap here looks bad, but mostly it's just rust staining from the reinforcing in the U-beams. So cleaned it up and all, and put superstructure replacement with wide flange beam spans. And here you can see the before and after similar photos of this bridge here. And so, as you can see, 24 more Simple for Dead, Continuous for Live, in addition to the 25 we had before. We've done 14 Simple for Dead and one complete replacement and one superstructure replacement by design bid build. So this is kind of in our lexicon now, where we do this where it makes sense. And on the left in Atchison County, you see this is a little bit more significant bridge. And it's got web walls for the intermediate bents there. There must be a drift problem here and so on. And you can see the migratory birds, the swallows, already taken a liking to this bridge there with all the swallow nest on it. And then the one on the right side there has what we call cast in place piles. They're closed in shell piles, steel shell, galvanized, and then we fill those with concrete. But good looking bridges that are going to last a long time because these are on routes that likely do not get salt like we do on our interstate highways. So 40 Simple for Dead, Continuous for Live replacements, 9 superstructure replacements by design build, an additional 14 and 1 superstructure replacement by design bid build since September. And we got currently 2 more in future lettings. So right now we've done 66 of these bridges completed or in progress. So what's next? We're going to continue to use this where it makes sense. Our engineering policy guide, I show a screenshot of the homepage of that. It's epg.modot.org, but we're going to add a section in our EPG. We've hired a consultant firm and the researchers at the University of Missouri Columbia to help us out with this. We're a little short-staffed in our development area, and so they're helping us work up the policy for putting this in our EPG, and hopefully should have that in there in 2026. Other states have used this. As I said, it was developed in Nebraska, and they built 3 bridges, 2 I-girder shapes and 1 box girder beam in the early 2000s. And I've discussed, we share bridges with Nebraska, so I know the bridge engineer there. And they're like, well, why don't we do this anymore? So they're considering doing it. Tennessee has done it. I show some screen grabs from Massman Drive over I-40 in Davidson County. The reason I put this screen grab is down here at the bottom, their compression blocks, they use a tapered block so that you can account for a little bit of distance issues with a taper, right? A wedge. So the reason that we got this is Wilson and Company saw this detail sheet in the Oregon Bridge Manual, and they have a section of their bridge manual, Simple for Dead, Load, Continuous for Live, Steel Bridge System, and the detail is DET 3620. And so they proposed this approved alternate standard, and we accepted it. And so the rest is kind of history, really. So with that, I'm going to conclude my presentation and